Good afternoon. I'm Pam Marcucci, Vice President of Programs at the Jacobs Institute, and I am very honored to welcome you to the 11th Annual College Internship Presentation. This cohort of 6 interns brings up the total number of alum to 57. Our past interns and our current interns have contributed to the JI in so many ways. They've improved our 3D printed models, educated high school students, and scoped out the competitive landscape. Their impact is felt long after they leave, and we're always bereft when they do leave. We also like to think that we have made an impact on them, giving them a taste of biomedical engineering, medicine, communications, education, careers. Some former interns have gone on to medical school, master's and PhD degree programs. Others are working in the medical device industry, and some are even working at the Jacobs Institute. We have seen art majors decide that they wanted to go into cardiac mapping, and students who were convinced that they wanted to become doctors decide on something else altogether. 20 of our former interns have remained in Western New York, having learned that they don't have to leave Buffalo to find innovation. So Mary Alice, one of our interns this summer, will be telling you more about our Interns to Innovations fundraiser that is raising money for the JI's educational programs. But I did want to mention it here as well. We are grateful for donations of all sizes. A $25 contribution will pay for a bus pass for 2 weeks for a high school intern. $100 will pay for a week of lunches for that same intern. So please snap the QR code and make a donation. You can get it at your phones now. We'll have this up at the end again and hope that we can count on your support. I also wanted to note that this year's costs have been covered in part by donations from these generous supporters for whom we are very grateful. So a few thank yous. I would like to thank Jessica Martinson, a JI Senior Program Manager, for so graciously stepping into the breach in educational coordinating and making sure that our internship programs were successful while also carrying out her project management duties. I'd also like to thank Katie Simon and Ariana Allman. Katie is our development manager and Ariana is our R&D engineer. They helped a lot with the intern presentations. Really appreciate their stepping in. Also want to thank Jim Herr, the JI's production services manager, for his help organizing today's production. Finally, I would like to thank all of the mentors who created impactful projects for the interns and worked with them so closely this summer to bring their projects to fruition. And thanks to all of you for coming today. I could not be prouder to turn the stage over to the JI intern class of 2024. Enjoy their presentations.
Hi, everybody. Welcome. It's glad to see you all here. I'm so excited to introduce the Jacobs Institute class of 2024 interns, and I can't wait for you guys to see what we've been working on this summer. Okay. So starting off, my name is Talia. I'm the I2R intern, and we're going to be taking you through the design cycle. So the design cycle, here it is. Yeah, there we go. You can see there's a bunch of parts to it. So each intern has their own space in this cycle, and we'll start off with just the idea stage. So ideation stage, well, what is the I2R? This is really where our innovation comes to life here at the Jacobs Institute. It's a place where Dr. Hopkins put his original vision into practice, a place where we can create, accelerate, and support medical devices, particularly in the vascular space, to help treat diseases in Buffalo, New York, and around the world. So why here? Buffalo has a great place you guys are sitting in right now. Above us is a world-class research institute, and below us is a state-of-the-art vascular institute. Dr. Hopkins envisioned the first multidisciplinary hospital in the United States. Why? I'll tell you. Buffalo has a shocking rate of 23% higher stroke rate than national average. Last year, we saw 2,200 stroke patients alone. Let that sit in. Like 2,200 patients came here for our support. This place has a lot of cool people. We have engineers, we have physicians, we have researchers, and we have the doctors that are actually performing these procedures. So my project specifically, I worked on frameworks for these early stage innovation projects, and they serve as living documents for our reference and engineering team. So the documents that I made were competitive analysis, a business case, and a user needs. We'll talk about the business case and the user needs, but for the most part, I'm going to be taking you through the competitive analysis documents, and you'll see what that looks like. So competitive analysis documents are really to understand what devices are already in the market. So we looked at ways to reduce time and cost, and a way for us to see what the demands are in the market just so we can meet them. So think of this document as like you're baking cookies, you're so excited, but you really need a grocery list. You might forget your vanilla extract on the way, you're making the cookies. Now you don't have regular chocolate chip cookies, and then you need to go back to this grocery store. So think of this competitive analysis document as a place for you to combine all of your important information, so your acquisition, strengths, weaknesses of the current market devices, just so that when you go ready for the device cycle, you have what you need later on. Okay, so I'm going to be taking you through a hypothetical case of an intracranial aneurysm. All of the stuff that we're talking about here is public information, but for the most part, the I2R does do confidential products. But for this particular instance, I'm going to be showing you through one of them. So we'll do an intracranial aneurysm. So, okay, you might be thinking, well, what is that? So an intracranial aneurysm is a ballooning from a weakened blood vessel in the brain. There already are solutions out there. So there's intrasaccular devices, coiling, and clipping, and I'll take you through a few of those. Okay, so these are already existing devices. We have the web, which also fits inside the intrasaccular aneurysm. You can see there that the blood flow will go to the right and to the left, as opposed to filling up the aneurysm itself. What we don't want is the aneurysm to rupture, because that creates a hemorrhagic stroke. So kind of just that background on there. We also have the contour, which is another similar device that sits inside the intrasaccular aneurysm, and this also creates flow diversion for blood. We also have the Galaxy G3. This is kind of a separate device. This is a coil that packs the aneurysm, but is also for flow diversion itself. And our last one is the most invasive, which is the clip, which is open brain surgery to kind of seal off that aneurysm from the rest of the body. For this case in particular, I'm only going to be talking about the most non-invasive ones. So we'll do the web, contour, and the Galaxy G3, just so you can see what the competitive analysis looks like. But that's how we are grouping these. Okay, so it's really important to look at a few things. We have novelties and intellectual properties, so what really makes these devices on the market really unique. The web is the first to market an intrasaccular aneurysm device, so we want to note that. And for the coils, it's greater cost efficiency. So we're really comparing two different devices and retrospectively. Intended use, we also want to make sure what the intended users for the devices are, as well as acquisition and cost. So who has already had in the market, who already has one of these devices, and who is looking to purchase one. If you can see acquired for $280 million and $530 million, we can see that there's a huge revenue potential for intrasaccular aneurysm devices. Nobody has $500 million laying around, so this really creates a lot of revenue. So for some of the other things that we look at benchtop testing to verify and validate that these devices are being used properly and that they're creating the results that we are looking for. For regulatory pathways, we want to know what our competitors are doing and how we'll get to the same place, or what have they done in the past that didn't work for them that we can capitalize on and make it sure that we do it right the first time. And weaknesses. So this is really where the gaps are in the market that we're looking for. Where are the unmet needs that we're trying to fill? So now we're going to talk about a little bit behind the user needs and business cases. These are also separate documents that I created to help our engineering team kind of put together all this information in one place. Not everybody has, if you're in an engineering background, you might not exactly have the business background, but it's kind of just like a brief introduction. So we'll go through first the user needs. So usability engineering and clinical adaptability. The physicians are already using these devices downstairs. We want to make sure that when we give them a new device, or there's a potential for a new device, that there's actually a reason that they're going to use them. We need to prove to them that the device that we're creating or we're potentially looking at has a better outcome for patient health outcomes. Excuse me. Okay, and then for the business case, it's really important to know who the stakeholders are, commercialization strategies, pricing and reimbursement, and revenue potential. We really want to know, is our device going to make a difference in the market, and how we can achieve that. So for the key takeaways, I learned a lot here. I learned that there's space in the market for new devices and unmet needs. Strategic planning can help in the process. So it really goes a long way. You're at the grocery store, you gather all the things you have at once to make your cookies, you're already set. There's no need for you to go back in time and kind of redo all that work. So that's what we're really trying to achieve here. It exposed me to the design control procedures and medical innovation. And it gave me a chance to really use my engineering and my business background to combine it into one project and really take the innovation stage all the way to market. And my last key takeaway is that the JI is going to get a whole lot busier once I figure out what that question mark is and make my $500 million device. So I'm now going to pass it off to Angela, and she's going to be talking about the development of vascular models. Take it away, Angela.
Hi, good afternoon, everyone. I'm Angela Altamirano. I'm one of the engineering interns this summer. So Talia just talked about the I2R, idea to reality, but I'm going to dive a little bit deeper on the steps in between, specifically device testing with our vascular models. So why are models important? There are three main reasons why models are important. One, physician training. We want to make sure that physicians know what they're doing when they get to the surgical bed. If I put a catheter at this angle, I feel this pressure return to me. Two, device testing and industry partnership. Companies can come to us and test their devices on our vascular models, which allows them to have effective testing and get these devices quicker into patients. Three, individualistic patient care. People have different anatomies. People have different disease states too, and through making models, we are able to have a better visualization and understanding of the best treatment. What makes a good model? Not all models are created equal. How do we get from patient scan to JI models? We want to make sure that what they learn with our models are directly transferable to what they do on the surgical bed. So there are four main parameters that we really look for in our models. We want to make sure that they're anatomically accurate. They need to be representative of what we have in our bodies. Robust. We want to make sure that they're not just a one-time use. They can be repeatedly used and over a long period of time. Dependable. Every single physician should have the same user experience. Tactile feedback. As I was saying with the catheter, if I put it at this angle, I feel this pressure return to me. So this summer, the two, dependable and tactile feedback, the purple ones, I will be focusing on. Dependable. We want to make sure that our models are the same every single time we use them, right? So right now, after we use them for 2 hours, which is our average time, we mimic in vivo conditions, the blood flow that we have. We use that with water. So after these testing, we know that there is some degree of water absorbance. We don't know exactly what happens to our mechanical properties of the models and when it happens. So that was part of my project, quantifying how water absorbance changes tensile strength and opacity. So as you can see in the right image, at time 0, the models are really clear and translucent, but after some use, it starts to turn white and a little bit cloudy, which decreases our visualization. For opacity testing and quantifying how water absorbance changes visualization, I took a frame of Agilus 30, which is the material that we currently use in our models, and then we had a frame of Vero Black. This is important because when I look at light transmission, I want to make sure that the light isn't bouncing everywhere and refracting when I do testing. So I used a light transmission meter, and I'll kind of break down the machine. At the bottom, there's a light, and then there's a space for the specimen, or our Agilus 30 frames, to be placed in between, and at the top there's a meter, and that can detect how much light is transmitted and how much visibility was lost. Over a 2-hour time period, I was able to see that there's about a 20% decrease in visualization. This is really important to know, so we can tell people how our model changes, and also this will serve as a benchmark for how we can improve our models going forward. For the mechanical testing, I started off with taking a dog bone sample. This is pretty industry standard for tensile testing, and then I soaked them in a water bath for 2 hours at 37 degrees Celsius, which is our internal body temperature. And then I did Intern testing to see how tensile strength is changed. I'll talk a little bit more about the Intron and how it's used. So the Intron applies a load, and it pulls the model until failure, or until it breaks. So from 2-hour time period, after 15 minutes, I did testing, and I found that the models actually take more force to break after there's water absorbance. This is interesting because it's kind of representative of how our blood vessels are really flexible and compliant. So the second area of improvement, tactile feedback. Our bodies, our vessels, have blood flowing through them and are lined with slippery cells. So right now, we don't really know how we can mimic that blood lubricious nature of our vessels. Because right now we use a coating, but just like any coating, it degrades over time. So how are we able to achieve the same goal, a lubricious model, but in a more consistent way that doesn't have any degradation. For this part, I took a patient scan and I segmented it. So I took part of the internal carotid, which is between your heart and your brain. So I took a segment of that. I took the center line, which is the middle of the blood flow, and then I used the loft and shell features in SolidWorks to determine the vessel diameter and the wall thickness of the vessels. And then I made a frame to make sure it doesn't topple over when I do testing. So the four main interests of this experiment is one, the current coating, and then seeing how it is compared to two other potential additives that we can use. One, carbamethylcellulose, CMC, and two, methylcell F50. And then I use water as a control. So for the procedure, I took my vessel that I printed, and then I either applied the coating or made the concentration with the water and the additive, and I put that in the vessel. And then I did Intern testing. So this one's a little bit different than the tensile testing with the dog bones. Rather than having it pulled, I attached a catheter to the top of the instron, and I saw how much force it takes for the catheter to be pulled out of the model. And this is important because from using instron testing, I can do force comparative analysis, meaning that the less force it takes, the more lubricious our models are, which is the more ideal. So this is a big graph. I'll kind of break it down for you. So the smallest force, meaning that the most lubricious, is the most ideal. So CMC, we saw one of the potential different additives at time 0 and at time 120, so after 2 hours have elapsed, is very similar to what our coating is like at time 0, at the very beginning. This is the most ideal state. And CMC, through having it all at the same, means that it's pretty consistent, which is what we want. And then we also saw that methylcell F50, which is another potential additive, at the very beginning is pretty good, but not as good as CMC and our current coating at the very beginning. And then we also see that after 2 hours, our coating increases in force, meaning that there's some sort of degradation of the coating within only a span of 2 hours. And then after, we also saw that methylcell F50 at time 120, there's an increase in force, meaning that methylcell also isn't super consistent, which also makes us further believe that maybe CMC is a better option. And then the control, the uncoated model that just had water. So this really shows that we need something. The model alone is not good enough to represent our vessels in the lubricious environment that we need. So this is just the beginning. We can do further testing, puncture testing, seeing how much force it takes for a catheter to poke through our models, shear testing, and also just more opacity and tensile strength with the new additives we may decide to pursue. And then also through this testing, we can have more advanced modeling. We can have improved accuracy, meaning we really know how the model reacts over time, and we mimic that lubricious environment. We can also work with physicians and patients to further our models and make sure that we can represent multiple anatomies and disease states. And also through that, we can move forward to pushing the boundaries of our models and working towards more complex boundaries. So I'm going to pass the baton off to John, who's going to talk about how we're already pushing these boundaries and designing different anatomies. Thank you for your time.
Hello, everybody. My name is Jonathan Kay. I'm a summer college engineering intern here. And I'll be talking about how I've been working with the model development team, and we've been pushing the boundaries of vascular models. Specifically, I'll be talking about the project I've been working on, which we work to make a looks-like model of an arterial venous malformation. I'll go more into detail that later. Then worked on optimizing parameters for printing to get a works-like model of this AVM. And lastly, working on creating a AVM hybrid model. So first, what is an AVM? So I'll give you a second to look at this picture. This is what an AVM looks like in the brain right here. This is an enlarged. So what is an AVM? An AVM is a fast flow vascular lesion within the brain, and that is characterized by an irregular or complex connection between arteries and veins. And why this complex connection arises is because there's a lack of a capillary bed. So normally, as you can see right here, there's this capillary bed. That is the normal connection. But when that is gone, you have this big jumble of mess. And then furthermore, a lot of these AVMs, they're described to be congenital, so they arise at birth, but there are some medical conditions that are associated with it. Now, why are we why do we want to know more about AVMs? Why are they important to us? Particularly because the abnormal blood flow within the AVM is a big risk factor for stroke. So if it bursts, you can have a hemorrhagic stroke and have a brain bleed. So that is why we want to follow it and do more research within it. So this is what an AVM in a brain scan looks like, just so you guys understand and have a bit of reference. So now I'll go into the first thing that I worked on, which was the lookalikes AVM model. I'll have one of my fellow interns pass around the model that I made. I'll also pass one of these around for you guys to look at. So first, this video that you just watched was just a demonstration of the complex anatomy of an AVM, how small it is and how complex the nature of it is. So to begin with that, I first created edits using 3D software. These edits particularly were splitting in half, so having a top half and a bottom half, and then allowing holes for magnets to be attached. After that, we printed it using a digital anatomy printer. Here's a time lapse of the print, and we chose for the printer to use a clear magenta resin to allow for better visualization. So with that clear magenta, you can easily see the complex nature of that malformation. Next, there is the post-processing. So for post-processing, we have removal of the support material. So that includes using my hands to physically remove it, as well as using a chemical bath to ensure that any support material is gone. After that, I mixed a 2-part epoxy to allow the magnets to be attached. As you can see here, there's the magnet, the epoxy, and then the magnets go in the hole. And lastly, why is this important to us? This complete model gives us a better understanding of the complex anatomy and allows both clinicians and medical device engineers to just understand what they're working with. So next, now that we have this looks-like model, I'll be talking about how we optimize printing parameters to work towards a works-like model. So to begin with that, I first created a small vessel model. So this small vessel was just a straight line vasculature that was curved, but it was created with a size that is similar to an AVM to get a better similarity between printing. Following that, the small vessel model was designed to have 3 parts. So there's the outer shell, inner shell, and core. The outer shell being yellow, the inner shell being red, and then the core being blue. And those were made like that to allow for different materials to be picked, so you can have an ideal combination while printing. The inner shell and the core, so the red and the blue, both get removed. These are support materials, so they will get removed post-processing after printing and cleaning. So going into this, for the first print, there is the outer shell, which was the yellow. We have 2 materials, either FLXA 9950 or Agilis 30. And then, as you can see, there is the highlighted red number. That relates to a shore A durometer reading, which just correlates to a stiffness reading. So for reference, a rubber band measures around a 40 and a tire measures around a 70. So now that we have the outer material, there's the inner material, which is the support 706, which is just one of the support materials we have. And then lastly, the core. For this print, we chose air. And as you see post-printing, there is a cloudy ring left over after post-processing, indicating to us that this support material, the 706, is not being removed properly and still being left in. So then we went again and printed it, but instead of having a air core, we had a liquid core. We saw that similar trend. That cloudy ring was still being left by. So then we looked again, and instead of doing a inner shell and a core, we combined those 2 together to print with a support material called pure gel, which has a consistency of like toothpaste. And once that was printed, we saw that there was no residual support material inside, and that's a trend that we liked. So we wanted to follow this and iterate on it. So we reprinted again, but now instead of using support 706 as the inner ring, we have just the pure gel as the inner ring, and then the respective air and liquid, and then pure gel by itself. And throughout all these prints, we saw that there was no support material left over. Everything cleaned easily. There was flow. So this was the ideal support material that we found for printing with small anatomy and such complex anatomy. So now that we determined what an ideal support is for such small anatomy, I'll go into a little bit of the network and prevalence of an AVM. So first, for an AVM, there's feeder arteries. As in the name, they supply blood to the AVM, and they can occur in 3 main locations. There's the middle cerebral artery, the anterior and posterior. And then along with this, with the locations, there's a quantity. So in cases, you can have single, double, or more than 2. And a majority of the time, about 45% of the time, it's 3 or more. And then just so you have an understanding, these are the feeder arteries. So there's a bunch connected to the main artery. And then Next, you have a draining vein, which your drainage vein is right there, and as in the name, it drains blood from the AVM. So now, giving an understanding of this, I'll talk about how I work towards the AVM hybrid model, and I will pass this around, which is the hybrid model that I worked on for you guys to look at. So why are we interested in this model? Why is it important to us? So first, I'll give you a bit of understanding of how complex this AVM is, the small anatomy, as well as just the complexity of the vasculature. So I first worked on integrating it into the brain scan with the middle, anterior, and posterior arteries. And after that, here comes our importance. So it's clinically relevant. It's a complete model from brain to AVM, and it is clinically accurate. So these are patient scans, and they were made into models. Next, it's good for clinicians and physicians. It allows them to have a training model that is realistic, so it gives them better practice with the cases that they are facing day to day. Next, it allows for companies to use a training model. So the current method for treatment of AVM is using an embolic glue, as you can see right here. What it's supposed to do is it dries and it blocks blood flow to the AVM. And these companies that are making these embolics, they can test these products with the test model to determine what parameters they need to look for, what they need to improve, and henceforth. And then next, following with that, the physicians that are using these products can become more comfortable with the actual product itself, so they can understand what parameters they need to look out for while they're doing these clinical cases. So now I'll actually go into the process of me printing and post-processing these AVM hybrid models. So first, the first print that we did, we have here, you'll see there's a little bit of cloudiness right here by the AVM. I'll point it out here as well. So for this print, what we did, we used a gel matrix support material. So that was used throughout the whole model. The gel matrix is a mixture of agilis cubes, so the outside of the vasculature wall, and then that pure gel toothpaste-like support that I mentioned before. And then after post-processing and doing some QC testing, with QC testing we used a UV light, UV dye, and then a UV light, right there. We saw that there's no flow throughout the AVM, indicating to us that the support material is not good, it's not getting cleared out of the AVM, and there's no flow. So we wanted to iterate on that again, so we did a reprint. But for this reprint, we split it in half. So the more complex top half was printed with just the pure gel that we identified earlier as being the optimal support, and then the bottom half as that gel matrix. So similar to before, we did QC testing, and we saw that there was flow throughout the whole model, and particularly throughout the AVM. And we like this. This is something that we wanted to see, we were hoping to see. And following QC testing, we did some fluoro testing, which is the grand finale of this project. So just to give a bit of a reference, this is what a AVM would look like under a X-ray or fluoro scan. You have your arterial feeders that I mentioned before, the feeder arteries. You have a draining vein, and then you have a nidus. The nidus is just the medical term that's used to reference that irregular connection between the arteries and veins. And then now for the fluoro testing, as you can see, there is flow throughout the entire AVM, which is what we wanted to see. And now I'll go a bit into the conclusions of our project. So ideally, first we saw that the pure gel support was the ideal support material for printing with such small vasculature and complex vasculature, such as the AVM. And then there's the AVM hybrid model that comes with a bunch of different benefits. It's useful for surgeons and clinicians to have surgical practice, so it gives a more realistic model of what they're facing with. It's good for product testing, so the companies that are making these treatments can test their products that they have and ensure accuracy. And then lastly, it's clinically relevant. It's a complete model from brain to AVM, so it completes the process. And then lastly, my time at the JI was a enriching experience. There was a bunch of skills that I learned. I learned a bunch within 3D modeling, a bunch within fluoro testing, and it was just a great time overall. And now I'll hand over the mic to Ellie, who will be talking about the synthetic clots she's been working on and the mechanical testing she's done.
Thank you, John. So today I'm going to take you through my summer internship, where I created synthetic clots to be placed in the models here at the JI to test new medical devices. I'm the last engineering intern to go, so I promise just one more presentation of random jargon I'm going to throw at you. Okay, so what's the motivation for my project? Well, it starts with a blood clot found in a patient. The problem with blood clots is that it's a clump of cells that get stuck in your vessels and restrict blood flow. The problem with this is that it could lead to a stroke. In order to treat a stroke patient, we need a medical device developed to take that clot out of the patient and for allowed blood to flow through the vessel again. So in order for this device to be used in a patient, we need to see if it's actually safe. So what do? We test it. So you can actually see a medical device being used here to pull out a clot from a patient. It's an animation. And so we have to test that device. Within testing here at the JI, just like Angela and John showed, we use realistic simulations. So like you can see on the right, these are realistic vascular models that we use to test the devices in. Within that model, and what I focus on this summer, is creating a synthetic clot. And you can see that in the device, those clots being used to see if the medical device actually works to be able to pull that clot out. So I'm going to talk to you today about two different types of clots that I focus on this summer. The first one is a blood-based clot. So the pro of a blood-based clot is that it's made from biological components, which is good because it's the same components of blood clots that we find in the human body. But there are a few drawbacks for this. So there's limited availability, low repeatability, and high cost. What do I mean by low repeatability? I mean that it's not the same every single time that we experiment on it. So every time we create that blood-based blood clot, it's not going to be the same every time. So what I focus on this summer is to reduce these different drawbacks. And I focus on a hydrogel-based blood clot. So although hydrogel-based blood clots are not built off the same components as real blood clots found in the human body, I did develop different tests to see if it's equivalent to human blood clots. So I developed some requirements, or I planned some requirements out for my project to creating that synthetic clot. So the first one, it needs to be readily available. It needs to be accessible, it needs to be low cost. Next, I want it to be safe. Doctors and engineers are going to be continuously touching that blood clot to put it into the models. So it needs to be safe and not harmful to the doctors and the engineers that will be using it. It needs to be easily adjustable. Like you know, blood clots come in different shapes and different mechanical properties. Some blood clots are calcified, meaning that they're kept in the body for a long time and are extremely hard. You also have red blood cell rich blood clots that are really soft and not left in the body for a super long time. It needs to be accurate. What do I mean by accurate? It needs to have the same mechanical properties as a real biological blood clot found in a human patient, so we can actually test if that device is safe to use in a patient. And it needs to be repeatable. Unlike the blood-based blood clots, we need it to be repeatable. It needs to be the same experiment every single time to see if that device is actually good to be used in the patient and competitive for market. So hydrogel selection. A hydrogel, it's a gel-like material composed of a network of polymer chains in a three-dimensional structure. What does that really mean? Why did I use hydrogels? Well, that's a great question because it's similar to natural tissues found in the human body through hydration and flexibility. It's also easily adjustable. Like I said in the beginning of my presentation, we need to make that blood clot either extremely hard, like a calcified blood clot, or extremely soft, like a red blood cell rich blood clot. So although this is a really small part of my presentation slide, this is actually a really big part of my project, creating that hydrogel-based blood clot. It was a big process and took a lot of problem solving. So the hardest part about this part of the process is that I had to take literature and put it into real practice in the lab. So once I created the different types of hydrogel-based blood clots, then I had to move on to testing to see, was it actually any good? So you can see on the right, this is actually one of the hydrogel-based blood clots that I created this summer. And so the first test I did was qualitative testing. And it's pretty simple, just like you see, it's a field test. You squish it. And in this video, you can see I'm squishing it, and I compare it to how it feels to real blood clots that we've created here at the JI. So the beauty about qualitative testing is that it's a multivariate assessment, meaning that you can test to see different parts and different mechanical properties. Is it sticky? Is it squishy? But although field test and squishing it is really fun, I also had to take some quantitative data this summer. So I also did and completed a shear, uniaxial compression, and an aspiration test, which I will get into later in my presentation. So the first test that I did was rheometer testing, and this is where I completed the shear and uniaxial compression test. So as you can see, the shear test in the middle picture, it's kind of, if you imagine rubbing your hands together, that feeling at the top of your surface of your hands is shear force. Or you can imagine two blocks sliding parallel across each other. Compression force is when you smush it, and it measures the energy it takes to deform the synthetic blood clot. For the rheometer that I used this summer, you can see in the upright picture, it's really, really small. So I had to take 8 millimeter diameter sample sizes of the hydrogel-based blood clots I created, which is about the diameter of a pen cap. The next test that I did, which was my favorite test, was the aspiration test, because that's really what we do in the model. We take something like an aspiration catheter to see how easily it can pull out the blood clot from the model. So I created this catheter in the lab with an engineer here at the JI, which was a really cool process to watch and to be able to take part in. And then this was my setup for my experiment. So I had a water bath, I had my blood clot in the water bath, and I had my catheter connected to a pump that sucked air out. And so this experiment we timed the ingestion of the blood clot to be pulled into the catheter. And I actually have a video of the experiment. So that white thing floating in the water, that's my synthetic blood clot, and you can see it actually gets sucked in by the catheter. So next is the most fun part, I think, of my presentation. It's the data analysis. Yay! So the first thing that I analyzed was the shear test data. So this looks a little confusing, but to clear it up, on the left you can see the patient clots, 1 through 5, and on the right you can see the synthetic clots that I created this summer. As you can see, they're right in the range of real patient clots found in the human body, so they're very similar in mechanical properties, specifically shear test. But the importance of doing multiple mechanical tests is that you can see different types of data, like this. Same clots, but super different, right? So that's why it's important that we do different types of data, or different types of tests. So it's the same setup. On the left, you can see the patient clots, and on the right, you can see the synthetic clots I created this summer. So the cool thing about this is that I noticed that some of my clots are super soft, that replicate red blood cell-rich clots, and some of the clots I created were fibrin-rich clots, or rather calcified clots, the ones that are super tough. The next part is the aspiration test analysis. So like I said earlier, it's the time of ingestion, which means the time it takes for the catheter to actually suck up that blood clot. So again, looks really confusing. But on the left, that is a blood-based blood clot. And you can see the data, it's all over the place, right? Not super condensed, not in one spot. That means that it's not repeatable. Every time we created that blood clot, it was a different ingestion time every single time that we did it. But the two on the right are blood clots that I created this summer. The difference between these blood clots is the weight volume percentage. So the one in the middle, you can see it's super repeatable, but the problem with this blood clot is that when we were testing it, something happened. It cored, meaning it was really soft. So it wasn't compressing and sucking into the catheter, it was coring it. So it was cutting it, and some of it was left on the outside of the container. So we decided to increase the weight volume percentage to make it tougher and to see if it would compress it a lot easier. And it did, but the problem is, I don't know if you can see what the problem with this one is, these little things at the top. So in a perfect world, I would like to delete them and ignore them, but since I'm an engineer, I have to address it. So the point about this is that I had to look at my protocol. What was wrong with my protocol? That's really important in engineering. It's perfecting your protocol so you can make the best possible clot, so we can make patients' lives better and release devices on the market that are good. So the problem with these clots is that the clots were getting stuck to the container. We don't know if it was because the gel solidified in a weird way or if it was getting suctioned weird. We're not really sure, but that's something that we look forward to doing in future tests and perfecting our protocol in the future. So the lessons I learned. I did a lot this summer, and it was really fun working on my project, but there's so many other things that I learned here at the JI. So I had a lot of equipment training. I was in the lab a lot, so I was able to get trained on the rheometer, the Intern, the laser cutter, the 3D printer, and so on. I also had extensive lab training. I was working with chemicals in the lab for a long period of the time because I was, mixing up the hydrogels, being a mad scientist. It was super fun. And then I think the most important thing that I learned this summer was the engineering mindset. And that I got from learning from the other engineers here at the JI. So problem solving, quality control, and data analysis. For example, when I was working with my hydrogel-based clots, after I was working with them, I was reheating them, putting them into different molds, and an engineer, actually my mentor, pointed out, Ellie, you should stop and see if the weight volume percentage is actually changing over a period of time. I was like, you're right, I should test that. So I dehydrated it to see if it changed over time after I let it cool. I want to also thank my mentor, Dan Rathbone, for being an absolutely amazing mentor and walking me through this whole process, giving me all the information I needed for this project, and just helping me all the way through. But I didn't just learn about engineering. There was also cross-collaboration with other interns here at the JI. I also had the opportunity to work with Mary Alice, our communications intern, which you'll hear from later, and I got to get interviewed and put on the Instagram and the LinkedIn. I also worked with Maddie, our education intern, and talked to the high school interns and told them about my college experience, but also listened to their experiences from their high school careers. And last, I also had the great opportunity to work in the, or not work in the OR, excuse me, to shadow in the OR and to shadow in the cath lab. And that was really cool because I got to identify different problems that us engineers can still fix. Thank you so much for listening to me. I'm now going to pass the stage on to Maddie, who's going to talk about the engineering education part of the design cycle. Thank you so much.
Thank you, Ellie, and hello, everyone. My name is Maddie Achtel, and I am the education intern at the JI this summer. I do not have a background in education, but in healthcare management. Today, I will be talking to you about what I did at the JI this summer. Education at the JI comes in three forms. The first is what you see here, the college internship. The second was my main project this summer, the high school internship. And the third, one of which I got to run this summer and was part of my project, which is brain boot camps. These typically run year-round for about 4 to 5 hours throughout the day. Education outreach is so vital in Western New York because cardiovascular disease is at an all-time high. Heart disease is the #1 leading cause of death in the United States. It causes 1/3 of all deaths in New York State. Stroke is the #5 leading cause of death in the United States and is the #1 leading cause of long-term disability. If we look here, you can see that the average for heart disease in Western New York is a lot higher than the New York State average, which is the red, and the US average, which is the gray. And if we look even closer at all 8 counties in Western New York, you'll notice that each individual county is higher than the national average for heart disease. These numbers are why cardiovascular disease education is so important in Western New York. My project, running the Jacobs Institute high school internship and a brain boot camp, gives the younger generations the chance to be educated about heart disease and stroke. If we start by educating the younger generations about the signs and symptoms of stroke and cardiovascular disease, this will give the younger generations a chance to recognize the signs and symptoms and how to prevent it, and eventually, hopefully, these numbers will start moving in a more positive direction. So, way back in 2022, I was a high school intern here at the JI. So when I got to the JI on my first day, I was able to kind of lead the way with my project. And so this year and last year were different than past years. In past years, it was just a two-week program where we had about 20 to 21 students, and they were here for 2 weeks listening to lectures, shadowing in cath lab, doing BME activities, taking tours. And this year and last year, there was an extra 5-week component where select students were selected to participate in lab placements in Western New York University lab skills. And so this year we had 21 students for the 2-week program, and we had 5 students placed in 4 different labs for this extra 5-week program. We had 21 students from underserved areas in Western New York. We choose from underserved areas because these are the most important areas to educate, as they tend to have the worst health outcomes. During the 2-week program, the students had the opportunity to hear from doctors, nurses, sonographers, physical therapists, respiratory therapists, and many more about their career and how they got to where they are today. They got to shadow in cath labs, practice on the JI surgical simulator, and take a tour of the Jacobs School of Medicine. We had 19 guest speakers this year. We had 6 different organizations represented by the guest speakers. We had Kaleida Health, UB, Jacobs Institute, and one from Honest Health and one from Key Bank. These were just some of the guest speakers that came and spoke. We had doctors, respiratory therapists, engineers, sonographers, physical therapists, and many more. So, what makes this year different? Well, in past years, we have given the students a list of research topics to pick from, and they would decide with their partner which one they would like to do. So this year we wanted to give them a real-world problem to solve. We decided originally that we were going to go with 3 problems, 2 of which I created when I got here at the JI this summer. Then we realized that 3 problems was pretty ambitious, so I condensed the 2 I created down into 1 problem. And instead of, in past years, how they've done a 5-minute TED Talk style presentation, we extended the time to this year's 7-minute TED Talks presentation, so everyone could get about 1 minute to present. And we split them up into larger groups, 7 in each group, so we had 3 groups. And the problem that I came up with was called Pathways of a Stroke Survivor. So we came up with a fake patient scenario where a 53-year-old male patient suffered an ischemic stroke in his parietal lobe. He was being discharged from the hospital soon, and he was going to need occupational therapy and physical therapy upon his release, and his wife was going to become his full-time caretaker. He also had medication that needed to be accounted for because after you have a stroke, doctors use medication to minimize the risks of having another stroke. There are so many different paths a stroke survivor can take once they get discharged, and taking small steps to improve your health and learning the impacts and the warning signs of stroke can go a long way in preventing stroke and improving stroke recovery. Family member caregivers carry a heavy burden. Caring for someone is a full-time job, and so we wanted the students to really realize that caregiving played a massive role in stroke patient recovery. And so there are so many different pathways a stroke survivor can take upon their release, and we wanted the students to also grasp that. Students also got to strengthen their soft skills like communication, collaboration, research, public speaking, time management, and organization. If we look here is few of the solutions that the students came up with. The first is what you see here, JI Post-Stroke. This is a website where stroke survivors and their caregivers can come to and easily contact their providers. And the second is an app called Halo Stroke. This is where the hospital, patient, and caregiver can all easily access and make appointment reminders, make appointments, set medication reminders, and so on. The third group created a rehabilitation facility. This would be located in the heart of the city of Buffalo and would provide free transportation to and from the facility to eliminate that access barrier. We had student satisfaction surveys to assess the viability of our program. I created a pre and post survey for students to fill out at the beginning and the end of their time with us. 89% of the students found that this internship was a complete success in their eyes. Everything from top to bottom was perfect. 94% felt confident about pursuing a career in STEM after the internship, and 100% of the students after the internship were interested in pursuing a career in STEM. So this is probably the most impactful part of my presentation and my project, student testimonials. After reading these testimonies and going through the student satisfaction surveys, I was truly inspired, and it really sunk in that I did this. I organized and effectively ran this high school internship program. I was super nervous coming in because I did not have a background in education. I didn't know how I was going to do that without this background, and then I realized soon that it wasn't about having a background in education. It was about how well I connected with the students. My goal coming into this was help guide these students and be a resource for them to discover what career in STEM they would like to pursue, and also be a role model to those students that do not have it all figured out, because you don't have to have it all figured out. Newsflash, nobody actually has it all figured out, and if they do, they're lying to you. And I thought I wanted to be a doctor. 3 major changes later, I'm now on the business side of healthcare. So after reading these testimonials and looking at the student satisfaction surveys, it really sunk in that I did this. I effectively ran and organized this high school internship, and I guided these students to realize their careers, which career in STEM they would like to go into, and open their eyes to all the different careers in STEM that there are. So now, I'm going to be passing the mic on to Mary Alice to talk about the funding and promotion behind the education programs.
Hello, everyone. My name is Marielle Skutnik, and I am the Communications and Philanthropy intern here at the JI. However, I don't have a communications background. I'm a journalism major, which played a large role in the execution of my project here this summer. So, after hearing about what all my fellow interns did here, you might be wondering where I come in and what my job was. Well, my project was to create and execute a fundraiser for the 2025 summer internship programs. In order to do that, I developed digital strategies to help spur the fundraiser and boost engagement on our social media. I also contributed to our quarterly newsletter and helped create a grant application that we submitted at the end of June. So, first I'm going to talk to you about why philanthropy here at the JI is so important. The JI is a nonprofit medical device innovation and education center. And as Maddie has already spoken to you about, we offer unique education programs for both high school and college students. Now, we aim here to eliminate access barriers within those programs. In order to do that, we provide lunches for all of our high school students, because when a high school student comes here and they don't know where their next meal is coming from, all they're focusing on all day is their hunger instead of the work that they could be putting toward their education and the program that they're supposed to be focusing on. So we eliminate that. We provide bus passes if needed, because not every student has a parent who can drive them to and from this internship every day or a vehicle in which they can drive themselves. We also pay our students a stipend so that they don't have to choose between working a summer job and advancing their education. In order to do all of those things, we need funding, which is exactly where I come in. Now, I'm a journalism student, so throughout my time, I've written quite a few articles. So the way I approached my 10 weeks here is the same way I would approach writing an article on a topic that I'm not really well versed in. I don't have a lot of experience in the medical or healthcare field, so as I approached this, I had to learn all about everything that was happening here at the JI. And the first step would be to conduct research and interviews. I had to get a well-versed, well-rounded picture of everything that was happening here. So the first step for me was understanding my role. So I read Pat's grant applications and also contributed to one that we submitted at the end of June. This helped me to understand philanthropic language in which I would have to put toward the fundraiser that I created this summer. That next step was watching my fellow engineering interns work in the labs. This allowed me to see the type of innovation that's happening every day here at the JI. After that, I got to see that medical innovation that's happening here take its next step forward and get tested. I got to see a doctor test that technology and see what works and what doesn't. And then the last step of that was shadowing a neurosurgeon. Right in the floor below us, I got to see a doctor use that technology that we're developing and testing here used on an actual patient. As a journalism major, it was pretty crazy to see a human brain right on the table. I was like, whoa. That next step would be to create an outline. So I created social media posts to help boost our fundraiser. Now, I created the hashtag Intern to Innovator, which is what our presentation here is called. And I use that hashtag on all our posts to help boost engagement and hopefully help reach more networks by using that hashtag. I also created an initiative called Takeover Tuesdays, in which every Tuesday for the month of July and the first week of August, one of our interns would take over the Instagram and showcase what they're doing here at the JI, to show people that the projects that we're working on aren't just busy work. It's a serious project that is going to be helpful in the work here that we're doing at the JI. Lastly, I contributed to our quarterly newsletter. As a journalist, this might have been my favorite part, getting to write articles. That was really much in my realm. As Maddie has already told you, she started here as a high school intern and then came back as a college intern. That story is so incredible because someone experienced this whole internship as a high schooler and then decided that she was so inspired that she wanted to come back and help those same high school interns discover what they wanted to do within the healthcare field. The next step would be to curate an angle for your story. So, how do we draw this fundraiser back to our main goal of the JI education programs? The goal of our education programs, as Maddie has already stated, is to expose students in the Western New York area to different careers in STEM and healthcare. So how do we go about explaining how this goal benefits the Western New York community? Our high school and college intern programs aim to uplift youth, young adults, and low-income families in the Western New York community. We aim to make our programs both inclusive and diverse, with over half of our students coming from Buffalo Public Schools in underserved areas. I firsthand got to see these students be inspired and encouraged to pursue careers in STEM. Now, this inspiration and encouragement to pursue a career does not only benefit these individual students and their families, but it also holistically benefits the entire Western New York community because it helps to mitigate the healthcare workforce shortage that we're currently experiencing here in Western New York, and it also helps to improve overall healthcare benefits for the entirety of the Western New York community. Now, this program showcases to students that there's a place for everyone in the healthcare field. You just have to find the area that you're most interested in. Because as Maddie has already stated, healthcare doesn't just mean doctor or nurse. There are so many other opportunities available. Now, the last step is to publish your story. So if you take a look at this giant QR code on my screen right now, if you take out your phone, open your camera app and scan it, it will take you to our fundraiser. Our CEO, Dr. Siddiqui, is offering today only that he will match every donation up to $1,000. We're currently at $600, so we're only $400 away from reaching that goal. I just want to say that this internship has been so inspirational for me. One situation that specifically stands out to me was my opportunity to shadow in the OR. As a journalist, getting to see an actual human being on an operating table and getting to see a human being's brain was incredible. My fellow intern Talia and I would both probably say that that experience was one of, if not the coolest experience of our entire lives. Getting to have that experience and then seeing high schoolers also get to have that experience was incredible. I think about myself as a high school student, and if I had had that experience, I probably wouldn't be standing in front of you today as a journalism major. As Pam continuously jokes to me, I better watch out because after this internship is over, I might be doing a full 180 on my career. So I just have to say, I really do hope that you will consider donating to our fundraiser so we can encourage future students to also pursue their careers in STEM. Throughout my 10 weeks here, I have gained valuable skills that will help me in my future journalism career. I've learned the power of storytelling, not just in the media, but in driving community engagement and support for vital initiatives. I will now invite my fellow interns back up for questions, and I thank you all for being here.
So if you guys have any questions, me and Ariana here will, you can just raise your hand and then we'll pass you the mic just so we can catch it for the people watching online.
So before we do any questions, we just wanted to take a minute to thank all of our mentors for the time that they took investing in us and our futures, because without them, these 10 weeks wouldn't have been possible, and you guys have helped us reach our career goals and just helped us along the way so much, so thank you.
I had a question about the lubricity testing. I was just wondering, on the chart that you were showing when it was showing the different coatings and how they were impacting the lubricity of those vessels, what would like a human blood vessel have looked like on that chart? So like what were you trying to replicate?
Yeah, when I did literature review with CMC specifically at the same concentration, the actual like blood in terms of viscosity is slightly lower. In the span of my 10 weeks, I would have liked to look at other concentrations, but I was more interested in seeing how Methocel and CMC were comparative to then pick which one. So it is slightly lower based off literature, especially with viscosity. So that's, yeah, it's slightly lower.
Excellent, thank you. And I have one other question, if you don't mind. So looking at the printing, when you have the different core material in the middle, what is the benefit of doing like the air or the liquid in the middle instead of having it solid? And obviously you can't have the whole thing be air, or I'm assuming it would collapse, but I was just wondering like, what's the benefits of each of those and why would you pick one or the other?
Yeah, so the idea for that was with the newest like materials that we were given, it allowed us to expand what we could do, what we could print with. So air wasn't an option not too long ago. Liquid wasn't an option not too long ago. So we were just trying to see what an ideal combination would be. So it was just a matter of testing and seeing what worked, what didn't work. And through that, we saw that the air and the liquid wasn't as effective as just a pure gel, but it does provide some benefits. It's more case specific. So if you have more of a complex anatomy, pure gel might work, but if you're not as complex, there could be benefits for air or liquid. And then also the air and liquid are much easier to clean out than like the Support 706.
Thank you all for the presentation. I have a question for Ellie, talking about your blood clot technology. I found it to be very interesting. And assuming it becomes a standard in practice, do you think it would be able to effectively be made at scale, assuming, well, to meet the demand of the medical devices industry?
That's actually a really good question because the blood-based clots that we use now in the models, they're extremely expensive and it's hard to make them, especially in bulk. But what I actually did this summer is I had to do a lot of problem solving with creating my hydrogels, and I kind of like 3D printed something to like hold beakers and stuff because I was making them in smaller containers. So I actually at the end of the summer was able to make like more of a bulk set of them. So I think that in the future with more research and more practice with it, that I think that we would be able to get to that level.
Thank you.
I would just like to compliment you, the sophistication of your presentations. And I've been to quite a few through the years, and they just get better and better. And you don't even realize that without a note that you're presenting so clearly. I didn't understand every single thing that you spoke about, but I'm amazed at your energy. You're just such a hopeful group. And I'm so glad you found this place to get started on the wonderful lives that are ahead of you. I wanted to ask how you found out about the Jacobs Institute internship program.
Oh, I just found out about it. I was looking for a summer internship for the communications department, and I thought that this one would be really special and unique compared to something else that I could be doing.
Okay.
Yeah, I was a high school intern, like I said earlier, and I kind of heard of the JI at first from my mom. Shout out, Mom. So that's how I heard of the JI, because she worked right below us at the GVI. So yeah.
I think for me, especially as an engineer wanting to stay in Buffalo because it is such a beautiful city, I think that Jacobs just stands out because it is one of the only medical device companies here that actually works on devices here in the area. So that's what drew me to Jacobs. Also, I actually did research upstairs with Dr. Yunitsa, so I also heard about JI through there.
For me, so for being a UB student, the BME department, or the BME club, tends to go to the JI for tours. So I've been at, I think, 2 or 3 tours through my time at UB, as well as I knew 2 former interns. So it was just mutual connections, as well as just coming here to visit, just grew my interest in wanting to work here.
Yeah, so I'm actually not familiar at all with the Buffalo area. I'm from California, but I go to school here in New York. So in one of my classes, we had like an orientation with other like PhD students and master's students at my school, and one of them is a former intern, so she spoke about her experience, and I was like, I want that opportunity too.
I heard about the internship because biomedical engineering is kind of a niche major. It's only like 12 years old at UB. There's only so many places that you can really take innovation and biomedical engineering and combine them, so that's when I found out about the Jacobs Institute a few years ago, and have wanted to do the internship since.
That's very helpful. It's not one place that you found out about it or the website or something. But anyway, I'm so glad you found it. So grateful for all you have accomplished.
Thank you.
Thank you.
I actually have a phone-in question. Tyler, one of our engineers, was like, can you please ask this question for me? So if your time here was extended, what would you want to work on next?
I guess I'm going first. But I would say one thing that I would definitely do if I was here longer was take more opportunities to shadow. It was just the coolest experience of my entire life, and I just would love to keep doing that.
I think that I would also say the same thing, take more time to shadow. I only got to shadow once because the high school internship and working on the brain boot camp kind of took up the majority of my time here. So I definitely would say shadowing.
I would continue my project. So like you saw at the end of my presentation, that there's still some more things to accomplish to actually use it in the models here to test different devices. So I definitely continue my project.
Similar to what Ellie said, I'd continue the project. So for the AVM, or the hybrid model that I created, that was just one scenario where the AVM could be connected. There's a bunch of different ways you can connect the AVM to the different arteries. So definitely want to explore that and see how that reacts with the flow and stuff of the model.
Yeah, just like the other engineering interns, I would also want to continue my project. Connecting the results from the lubricity testing back to opacity testing and seeing if there's changes, and also maybe expanding my vessel model and not just a segment, but rather something more representative of our full vasculature.
There's always I2R projects coming in, so I think I'd want to work on whatever next is coming in and just see from there where it goes.
All right, so I want to do something kind of fun. How many former interns are here? Can you please stand up? Katie, Max, Serena, Claire, Madison, and Connor, and Ariana. So we've managed to keep them close by. So that's fun. Thanks, you guys. And now I'd like to invite you to some refreshments across the hall in the Jacobs Institute. We will leave up the QR codes. We'll put back the QR code. Please feel free to download it and make a donation for our wonderful education programs. And thank you very much for coming today.